Hello everyone. Today I feel happy to reach the 25th lecture. Okay, so this is a milestone for us. Anyway, so we have been discussing the 3D system, and today we are going to discuss the rigid rotor, diatomic rigid rotor, and its associated energy levels. So why we would be discussing rigid rotor right from the particle in a 3D box, once we get into the solutions, it will be somewhat clear for us. But here in this lecture, we are going to introduce a new coordinate system. So far we have been familiar with Cartesian coordinate system x, y and z, and with mutually 90-degree angle between them. But now we have to shift to a polar coordinate system. Remember, this polar coordinate system is also known as the spherical coordinate system. So why do we need a polar coordinates? Because like if you think about hydrogen atom, it's a spherically symmetric thing. If we think about a rigid rotor means two atoms separated by a fixed bond length, and they are rotating in 360-degree angle. So this is some kind of spherically symmetric object, the rotation. So here in any spherically symmetric environment, this Laplacian operator is only useful when we express that in polar coordinates. So in other words, the Laplacian operator is no good for Cartesian coordinates when we talk about some spherically symmetric environment. So we have to find the expression for the polar coordinates, and then we have to find an expression for lambda square, the delta square. Alright, so how do we convert x, y, z in terms of r, theta and phi? So let's assume that this is vector r. Okay, so this is situated at an angle theta from the z-axis, and then we take a projection of r on xy plane, and then we have to express what are x, y and z in terms of theta and phi. Alright, so let's first define the limit of theta. So theta can vary anywhere from 0 degree to 90 degree, and phi is rotated on xy plane. It can vary anywhere from 0 degree to 360 degree. Alright, so now here z is equal to r cos theta, the component of z, means a component of r towards z direction. And then similarly for x we can define the projection of this thing here. Alright, so that means if this is cos theta, so this should be sin theta. So r sin theta, and then cos phi should be x. Alright, and similarly y is equal to r sin theta sin phi. Alright, so along with that, it also satisfies the following conditions, that is r is equal to root over of x square plus r is equal to x square plus y square plus z square, and cos theta is equal to z divided by root over of x square plus y square plus z square, and also tan phi is equal to y divided by x. Alright, now if we take all these values, expressions like z is equal to this, x is equal to this, and y is equal to this, an expression for tan phi, alright, as well as cos theta, whatever, then we, by following the chain rule, let me write the chain rule of differentiation. Okay, so following the chain rule of differentiation, we can arrive at an expression for Laplacian operator. So for the Laplacian operator in Cartesian coordinates, once again we can write that. Alright, that's what we know. and then we have to convert this expression in terms of r, theta and phi using these relationships and the chain rule of differentiation. Alright, if you are unable to follow what is the chain rule of differentiation, please follow any standard physics or mathematics textbook. So they will show you how you can convert the derivation of converting Cartesian coordinates into the polar system. Anyway, let's assume that we have successfully converted this thing into the polar coordinates. So let's write the expression. So in polar coordinates, the expression for Laplacian operator becomes something like this: 1 over r square del del r square del del r, alright, and then theta and phi becomes constant, plus 1 over r square sine theta del del theta of sine theta del del theta, alright, here r and phi constant, plus 1 over r square sine square theta, okay, and del 2 del phi 2, where r and theta is constant. Alright, and so that becomes our Laplace expression for Laplacian operator. So I'm going to mark the entire operator. So you see, it's a kind of a pretty long expression, alright, and since the derivation is pretty lengthy, so it is worth remembering it. Alright, so let's all try to remember the expression for this Laplacian operator in polar coordinates. Alright, so now since we got the final results from memory for the time being, then we are going to apply that into the rigid rotor. Okay, so we are going to find out the energy levels, or in other words the solution, that means the wave equation for a diatomic rigid rotor. Alright, so let's clean the board and work towards that direction. Okay, so we have a diatomic molecule here with two different masses, M1 and M2, and this should be the center of rotation around which so we can think about that this is the center of our axis of rotation. So around this the molecule rotates, so it goes to the center of mass here, and the distance or bond distance between the two is r, and here r is constant. That's why the term rigid comes from. Rigid means the bond distance is fixed while the molecule undergoes the rotation. Alright, so now the question is, how can I express the detailed Schrodinger equation for such diatomic rigid rotor? So the Schrodinger equation says that H psi is equal to E psi, alright, which is the time independent equation. So the question is how we can find out the Hamiltonian operator for rotational energy. Remember one more thing, that this rotating molecule only has kinetic energy. It has no potential energy. So once again we can write that the U, potential energy, is 0 for this case. So for Hamiltonian operator it is the kinetic energy operator. Okay. So we have seen that this is equal to minus h cross square divided by 2m, the Laplacian operator for linear kinetic energy. Means kinetic energy associated with linear motion. But here we have a rotational kinetic energy because the molecule is rotating. It is not undergoing any linear motion. So the question is, what could be the operator or expression? It is almost the same, very similar, but instead it should be minus h cross square divided by 2I Laplacian operator. Now the question is, why did we replace m with I? Alright, so here I stands for the moment of inertia. Alright, the I stands for mu multiplied by R. So mu is the reduced mass. Mu is the reduced mass. So R square. Yeah. So mu is the reduced mass of the system, where mu is equal to m1 m2 divided by m1 plus m2, and R is the distance between the two, or bond distance. All right, and in other words, the rotational KE, kinetic energy, can be represented as half I omega square. All right, just like half mv square I omega square. I corresponds to the mass, and omega square, omega is the angular velocity. All right, so then also there is another term, is called L, stands for angular momentum. So the angular momentum is the product of moment of inertia and the angular velocity. It's much like linear momentum, P is equal to mv. So here you see the term I actually replaces the mass of linear motion. All right. So if that is true, then we can further write this is equal to I omega whole square divided by 2I. So here I omega is equal to L, then we can write L square divided by 2I. Alright, so now we can understand why we have replaced M with I here in the Hamiltonian operator for rotational kinetic energy. So now the question is, can we write an expression for L square operator? Alright, so that means the square of the angular momentum. Alright, so here L stands for angular momentum operator. So of course from here, from this equation and this equation, we can tell. So the rotational kinetic energy is L square by 2I, and the Hamiltonian for kinetic energy operator is minus h cross square Laplacian operator divided by 2I. So therefore L square becomes nothing but minus h cross square Laplacian operator. So you see this L square is a important quantum mechanical operator. Alright, and like all other quantum mechanical operator, this is a valid quantum mechanical operator, and it fulfills all the conditions for a valid quantum mechanical operator. That means this operator is linear as well as this operator is Hermitian. Alright, so in this way, while we can find an expression for Laplacian operator for rigid rotor, we can also find the expression for the quantum mechanical operator square. Alright, so how we can find out the expression for the Laplacian operator for rigid rotor. So remember, we have already written the expression previously. Alright, so here we can start with h of the rotational. So h, Hamiltonian operator for rotational energy, where u is equal to 0, is equal to minus h cross square divided by 2m. And here we have to write the expression for the Laplacian operator. Now remember, this Laplacian operator we are going to derive with the constant r. So that means whatever the partial derivative of r, that means the del r part, that will vanish. Okay, so our thing would be 1 over sine theta del theta of sine theta del theta, alright, where we have already r and phi constant, plus 1 over sine square theta del 2 del phi 2, alright, where we have theta and r constant, alright, so we can write this thing. So this would become our operator for rotational kinetic energy, and this tells me that the L square operator is simply minus h cross square multiplied by this entire expression. Alright, so now we are going to write or start from h psi is equal to e psi by having this expression, and we are going to solve this particular Schrodinger equation. Alright, so let's clean the board and try to do that. Okay, so now I have written the Schrodinger equation using the entire expression for the Laplacian operator. So this is h psi theta phi equal to e psi theta phi. So now we have to solve it. So in order to solve, we have to just simplify the expression. So what we are going to do, we can multiply by minus 2m by h cross square sine square theta both sides, so that the expression becomes simplified. So, or if we do that, what we get is sine theta multiplied by del theta of sine theta del theta. You see, I'm not writing phi part constant every time because that is understandable. Plus we are multiplied by sine square theta, alright, so del 2 del phi 2, alright, and we have entire thing psi theta phi, and then we have, once we multiply by minus, there will be a minus sign, and we are now taking this part here, so it would have plus 2me divided by h cross square psi theta phi, everything equals to 0. Alright, good. So now what we are going to do is that we are going to write that in a further simplified form, that is sine theta del theta of sine theta del theta of, so this would be operating on psi theta phi plus del 2 del phi 2 on psi theta phi, and I'm going to replace this 2me by h cross square term. Sorry, I have missed a sine square part over here. Okay, so pardon me, I have missed the sine square theta term over here. So sine square theta psi theta phi is equal to 0. Alright, so what I'm going to do is I am replacing this thing as a constant beta, because I don't have to write so many terms every time. Then beta sine square theta psi theta phi is equal to 0. Alright, so by looking at this, you see this is a partial differential equation. Okay, so now we know how to handle this. So therefore, from our knowledge, we can readily express psi theta phi as a product of two independent function, which is g as a function of theta multiplied by f as a function of phi. Alright, so let's replace psi theta phi over here, here and here with g theta f phi multiplied by g theta multiplied by f phi, and then again divide both left and right side by the product of g theta f phi, the standard procedure. So let's see what expression we can get after we follow the standard procedure for the separation of variable principle. Okay, so let's write the variable separated form of this equation freshly after cleaning the board. Okay, so let's do it here. Okay, so let's continue. We have assumed that psi theta phi is the product of g theta and f phi. So if we put that into previous equation, so we get this expression. Okay, and of course after putting this, taking the partial derivatives and multiplied by g theta f phi on both sides, we get this variable separated form. So now let's see that this part is the function of theta only, and this part is again function of phi, and also this part is function of theta again. So what we see that a function of theta plus a function of phi becomes equal to 0, and we are already familiar of such situation. So we can immediately conclude that means the function of theta plus the function of phi should be is equal to 0 when the function of theta should be equal to some positive quantity, we can say m squared say, and the function of phi should be some negative quantity minus m squared say, and that should be is equal to 0. Alright, so what we do now is let's take the variable separated form and let's frame two more equations. Okay, so from this we can get that one, we can now copy this part, sine theta d of theta, this part plus beta sine square theta is equal to, according to our consideration, we can take that value as m square. Okay, and we can call it equation 1, and lastly we can take 1 over f phi d2 d f phi and f phi d phi 2 d 2, okay, plus m square is equal to 0. Alright, so we have this another equation. Alright, and with this, since we have got these two equations, so now it's our job how to find the solution of this one and this one. So from these two we can immediately recognize that this equation number 2 was known to us, and we have already solved such equations before. So out of these two, we would first focus on the phi part and let's try to solve it. Alright, so let's clean the board and start working out over here. Okay. Alright, so before we proceed, I think I made two mistakes in two places, so let's try to fix it. So one thing over here, so while writing by mistake I should have written d2 d phi 2. Okay, so this the double derivative of f phi is being taken with respect to dd phi, and here also that was the mistake over here. Okay, so please excuse me for this mistake. All right, so now it is all right. So this is the entire equation in the correct form. Okay, so now let's proceed. Okay, so now if we try to solve the equation number 2, so look at this equation. So we have solved this equation many times before. So if we do, you see, we will have two solutions, okay, for both the roots of m, plus m and minus m. So one of the solution is am into e to the power I m phi, and a minus m multiplied by e to the power minus I m phi. So here a m and a minus m are the arbitrary constants. Now look at here carefully. Since the motion is circular on the plane, so now we are trying to impose some kind of conditions. Okay, the condition is, there is only one condition. Since the motion is circular on the plane of phi, so you remember the molecule is rotating on xy plane or plane of phi, it requires the motion to be continuous. So that means over a full rotation of 360 degree, after we complete it, once we just go over 360 degree, we repeat periodically the same original position. So that means the function f, okay, sorry, yeah, the function f phi plus 2 pi should be equal to f phi. Okay, so this is clear from the condition. So now what we are going to do, we are now going to put this condition over here into here. So what we can write, that is we have a m multiplied by e to the power I m, okay, and instead of phi we can write phi plus 2 pi is equal to am e to the power I m phi. All right, so we are actually we have put this condition over here. Okay, so now this would give me, or if we can expand, am e to the power I m phi multiplied by am e to the power I m 2 pi is equal to am e to the power I m phi. All right, so here these two parts cancel out and we are left with, or am e to the power I m 2 pi is equal to 1. All right, now if we put the same condition, that this is equal to this, all right, or am e to the a minus m e to the power minus I m phi plus 2 pi is equal to a minus m e to the power I m phi. If we do that, okay, we would going to reach this conclusion is equal to minus 1. All right, so okay, hold on, there is some mistake over here. Okay, so what I'm going to do, I'm going to erase this part and let's correct the mistake. Okay, so the mistake happened was here, so it should be am e to the power I m phi multiplied by e to the power I m 2 pi is equal to am e to the power I m phi. All right, so these two part cancel out. All right, no, sorry, not this one. So these two part cancel out and this tells me e to the power I m 2 pi is equal to 1. All right, So this comes from the equation here applying on this solution. Now if we apply the same condition over this, alright, so we will get e to the power minus im 2 pi is equal to 1. Alright, so that tells me that if we join these two, we can get a general solution that is e to the power plus or minus im 2 pi is equal to 1. Okay, so how can we expand this expression? Because according to Euler formula, we have a trigonometric expansion for this expression. All right, so let's erase this part and write it. Okay, so now using the Euler's formula, we can write this part as cos 2 pi m plus or minus I sine 2 pi m, alright, is equal to 1. So now this expression, okay, whatever we have written, is equal to 1 is only possible. This is possible only when m value takes up the following: either m is equal to 0, or this is plus or minus 1, or plus or minus 2, or plus or minus 3. So plus or minus integers, etc. Okay. So therefore, now we get the final solution for f5. This is our final expression. So f5 is equal to am e to the power I m 2 pi, all right, or actually it should be am e to the power I m 5. This is, we are talking about the general expression, of course, where m is equal to 0, plus or minus 1, plus or minus 2, etc. Okay, so I believe you have seen such expression before, and the values, that is 0, plus or minus 1, plus or minus 2, may buzz a ring inside your brain, because we have seen the magnetic quantum numbers of atoms take up these values, right? 0, plus or minus 1, plus or minus 2. Okay, and incidentally we have also used that quantum number m here. Okay, so later we will find out these, whatever the m value that comes out, these are actually some quantum numbers. Okay, but here it is associated with some rotation, so this is a kind of a rotational quantum number. So anyway, let's finish this part. So this is our general solution, f5 is equal to the power im5, and then we have to find out the value for m, that means the normalization constant. So remember, this is one part of the solution. Okay, so as we have already mentioned, that psi theta phi part is equal to g theta multiplied by f phi. So what we are trying to do, individually we are trying to find a normalized expression for f phi. So how we are going to normalize it? So we are normalizing it following the condition that the limits are for phi 0 to 2 pi. Psi star means am star e to the power im phi star psi, or means f phi am e to the power im phi. Here we have d phi, okay, is equal to 1. It should be equal to 1. So, or since these are arbitrary constants and real, so we can take am square, all right, 0 to 2 pi, and e to the power im phi star multiplied by e to the power im phi. So it would come down to e to the power 0 means 1, d phi is equal to 0. So from here we can easily find out that the normalization constant is 1 over root over of 2 pi. So therefore, finally, we get our one of the 5 portions solved, that is f phi is now, so we can write this phi theta phi is equal to g theta multiplied by f phi is equal to g theta multiplied by this part 1 over root over of 2 pi multiplied by e to the power I m phi, where m is equal to 0 plus or minus 1 plus or minus 2, etc. Okay. So now finally we are down to the one part of the solution. So we have finally successfully solved f phi. So we have still to solve the g theta part. Okay. So I think that's enough for today. So in next lecture we are going to find the solutions for g theta, and we are going to find another sets of quantum number, and we will see how these two quantum numbers, this is the m and another type that we are going to find, these two govern the final solution, that means the final wave functions for a diatomic rigid rotor. Okay, so there are some heavy expressions and heavy derivations involved in this lecture, and I recommend you to follow this lecture with a pen and paper by dealing all the equations and derivations yourself, okay, without looking at the lecture step by step. So basically you have to do the derivation yourself. So keep practicing and see you in the next lecture. Till then, goodbye.